Oh ho ho! Hello! Have you ever wondered why Old Saint Nick is so plump? It's because of mass balance, that's why. All those milk and cookies are mass input to the system of my belly. There, some of them are converted into energy and nutrients as accumulation, as you can well see. And then some of it exits as a mass output. And there you have it, mass balances. Today we're going to learn all about it. Yeah, so as Santa just told us, mass balance usually has three major terms: a mass input to the system, a mass output to the system, and some change due to reactions that occur within the system. This is largely intuitive, right? Because the law of conservation of mass states that mass can't be created or destroyed, although it can be changed from one state of matter to the next, or changed from matter to energy even. So because of this, we'll write our equation in its general form as accumulation equals mass in minus mass out plus some change due to a reaction. And that mass in is just any mass that's entering our system. Mass out is just anything that's leaving our system. That reaction term, you'll notice there are two variables there. The R is just our reaction rate, or the change of concentration of the contaminant with time. And then the V is just the volume of our system. And accumulation is just whether anything is coming into the system that is not exiting, or exiting the system that's not entering. So a gain or loss in volume of our system. There are many scenarios to consider here. Based on your system, you may or may not need all of the terms in your accumulation equation. So that's why it's super important to define the boundaries of your system. Your system may be like a portion of a stream, or a lake, or even an aquifer system with soil inside of it and water.
Sometimes we will not have an accumulation term because we expect everything entering the system to also exit the system, like a section of a garden hose where all the water coming in will also flow out, and this is called a steady state. But in other cases, what is entering the system cannot exit and will build up and accumulate, and this is a non-steady state scenario. Sometimes we don't expect any reactions to occur, so we can leave out this reaction term. This means we have a conservative pollutant as opposed to a reactive pollutant. Depending on the system, you may or may not need all of the terms in the equation, so it's very important to define your system boundaries. It could be a stream, it could be a lake, it could be a pipe. You just have to be very careful and make sure to define that before you start the problem.
If we combine these possibilities, we come up with four different possible situations. The first of these is if we have a steady state system with a conservative pollutant. So in this case, we don't have a reaction term, and we also don't have any accumulation. So we just have our mass in minus mass out equals 0, or mass in equals mass out. For example, a stick floating down a river would be a conservative pollutant, since it's not reacting with anything in the water, and all the water flowing into the river is flowing out of the river, so it's a steady state system. So for a non-steady state conservative system, where we have a conservative pollutant, we do have accumulation this time, but we still don't have that reaction term because it's a conservative pollutant. So we'll just write it with our change in mass over time equal to mass in minus mass out. And that reaction term would just be 0. So an example of that would be like pouring salt water into a cup and taking one small sip. The salt does not react with anything in the water. It's just going to sit in the water. But not all the water and salt that enters that cup is going to exit that cup. Some of it will stay in that cup while you take that one sip. In a steady state system with a reactive pollutant, we're just going to cancel out that accumulation term. That goes to 0. All of that other stuff stays there. So we'll have mass in minus mass out plus our reaction term equals 0. So an example of a steady state reactive scenario is chlorinated water in a pipe with no leaks. All the chlorinated water that enters the pipe exits the pipe, but some of that chlorine is going to react with organics in the pipe or whatever else may be in the pipe. Our last situation, we have a non-steady state situation with a reactive pollutant. In this case, we have our entire general form. We have accumulation equals mass in minus mass out plus our reaction term. Everything's there, we don't cancel anything out. An example of this situation is chlorinated water flowing into an enclosed reservoir. In this situation, not all of the water entering the system is exiting the system. In fact, none of it's exiting the system. And that chlorine water may be reacting with some of the organics in that enclosed reservoir. And that's the end of this video. In our next video, we'll go into a little more detail about what each of those terms actually is and how we calculate that, in addition to talking more about what sort of reactions may happen and how we calculate our reaction term. See you next time.